So this is the example we stopped at last time. And so the example says, suppose the equation x cubed minus xy plus y cubed equal to 1 implicitly defines x as a function of y. So this is different. Usually we treat y as a function of x. So in this problem, I'm assuming x equals g of y. That is, x is a function of y, which means the y is the independent variable. It's the input variable, and x is the output. And here we don't know the formula for x explicitly. We're just given, this implicit definition that the function x, which is g of y, satisfies this equation. And so here, we're asked to find not dy dx, but the opposite, dx dy. So, we just move forward and use the theory. There's nothing really new here. We've just kind of changed the roles of the variables. So as I mentioned now, y is the independent variable or the input, and x is the dependent variable or the output. So to find dx dy, we're going to differentiate with respect to y and not x. So let me show you how that works. So if we look at this equation here, let me show you how we take the derivative of x cubed with respect to y, for starters. So starting with x cubed, and for me, it helps to remember here, I'm assuming that x is a function of y. So when we say x cubed, what we're really looking at is a function of y cubed. This is a composition. The inside function is g of y. The outside function is, being cubed. So this is the inside is g of y, and the outside function is something being cubed. So for the derivative now, so when I now want to find the derivative here with respect to y, because this is a composition of functions, we're using chain rule. And I'm doing derivative of the outside. So here, the derivative of something cubed, we bring the 3 down and subtract 1 from the exponent, so it's 3 g of y squared times the derivative of the inside. The inside function is g of y. The derivative of the inside is g prime of y. Now be very careful. When I say g prime of y, I mean dg dy. So here, the derivative we've taken is with respect to y, not x. So here, g prime is actually dg dy. And so if you want to write the derivative in terms of x, so here 3g of y squared, that's the same as 3x squared. G prime of y I can write as x prime. And it's very important to understand what the prime means from context. So when I say x prime here, I mean dx dy. And the slides I sent you may not have this. I added it at the last minute. So I wanted to emphasize that here, dx dy and the x prime, that they're the same here. This g prime of y, that's the same as dg dy. So we're using the same derivative rules, except we're trying to keep track of what the independent and dependent variable is. For example, if you look at this function, if we did the derivative with respect to x, the derivative with respect to x would be 3x squared dx, derivative of the inside, dx. This is if I'm doing an x derivative. And then we say, oh, well, dx is just 1, so the derivative with respect to x is just 3x squared. If I'm doing the derivative with respect to y, it's basically the same thing. First, I do the derivative of the outside is 3x squared. Then the derivative of the inside will be dx, not dx now, because I'm doing the derivative with respect to y. Instead, it'll be dx dy. And so then my final answer will be 3x squared, and dx dy isn't equal to 1. So here, I still need to write down, either x prime or dx dy. And that's why we're getting this derivative here. That's exactly, it's just a chain rule. And that's how you're getting this derivative. You can think about it that we always do chain rule. You know, it's just if I take the derivative of x cubed with respect to x and do a chain rule, it's boring. It's just 3x squared times dx dx. Derivative of x cubed with respect to y, 3x squared dxy. Derivative of x cubed with respect to t, if x were a function of t, 3x squared times dx dt. You know, so the chain rule is basically always in effect, and we just want to keep track of what's the variable we're differentiating with respect to. So the other term here that I want to show you is x times y. Here, x is a function of y is obviously a function of y, so we're going to need a product rule here. And so I like, you know, it helps me to think about x here is really a function of g of y. And so when I write this as g of y times y, and I'm taking a y derivative, yeah, this definitely makes sense. And it looks like there should be a product rule because you've got a product of functions of y and we're doing a y derivative. And so now derivative of the first times the second, the derivative of g of y with respect to y is just g prime. It's just dg dy or g prime times the second function, which was y. And then we do plus, copy the first function, which is g of y, times the derivative of the second function. So the second function is y. The derivative of y with respect to y, dy dy, is just 1. Right here, I'm taking the derivative of y with respect to y. I'm just doing dy dy, and that's where this 1 is coming from. So the derivative of the left-hand side looks like, the derivative of x times y, where x is being treated as a function of y, looks like g prime y times y plus g of y times 1. And now if I replace g of y and g prime with x, because x equals g of y, that's what the product rule looks like. Again, you know, just to emphasize here, the x prime, the primes here are with respect to dy. That's a dy derivative. When I say x prime, that's dx dy. So, okay, here's how I would do the problem if I was just doing the problem, right? Here I've written way more than I need to because I wanted to explain it. But if I was just doing the problem, here's what I would do. I would just, starting with the given equation, x cubed minus xy plus y cubed equal to 1, I'm taking the derivative of both sides with respect to y. Derivative of x cubed, derivative of the outside is 3x squared times the derivative of the inside is dxy. Dx dy, excuse me, or just 3x squared x prime. The derivative of x times y, I'm remembering x is a function of y and I need a product rule. So here I do derivative of the first, so derivative of x with respect to y is just dx dy times the second function, which is y, plus x times the derivative of the second function, which is just dy dy. And here I should put a minus sign and put parentheses here. And then finally, the last derivative for y cubed, the derivative of y cubed is 3y squared dy dy. So I don't even write anything down. And the derivative of 1 is 0. So here, if we check, here's my 3x squared x prime. That's the same as 3x squared dxy. And then we have the product rule here, minus parentheses x prime y plus x. That's exactly the same as this. Minus parentheses dx dy y plus x dy dy. Remember, dy dy is just 1. And the derivative of 3y squared, the derivative of y cubed is right here. 3y squared, nothing special there. And then the derivative of 1, it's a constant, so the derivative of 1 is 0. So that's the implicit differentiation. Now it's just algebra. Now I'm just collecting the terms that have x prime in them. Remember, we're trying to solve for dx dy or x prime. I'm going to move all the other terms to the other side. Okay, so be careful. This minus sign has to distribute. And then these terms, which will be a minus x plus 3y squared, gets moved to the other side. So I factor out the x prime on the left side. Here you get x minus 3y squared. In the notes I sent you, I had a typo. I had a minus sign here in front of the x, which is wrong. As I said, This becomes a minus when you distribute the minus, and then when we move it over, we lose that minus sign. So that's now corrected. 3x squared minus y times dx dy equals x minus 3y squared. And finally, I solve for x prime to get my final answer. So here, x prime or dx dy equals x minus 3y squared over 3x squared minus y. So nothing has changed here except we're now playing the game with respect to the y variable instead of the x variable. And you can think about it as we're always using chain rule. It's just that when I do a chain rule on x cubed, the derivative of the inside is trivial, right? The derivative of the outside would be 3x squared times dx dx. But if I was doing derivative of x cubed with respect to y, derivative outside stays the same, 3x squared. The derivative of the inside changes. Now it would be times dx dy, or x prime. So this is all about, getting away from the symbols and starting to think about these things more abstractly and starting to think about things more as placeholders. Doesn't really matter what the symbol is. It's just that, we play the game with the appropriate symbol. They're just placeholders. So here's the last example I wanted to do. This is a little bit complicated. It's good for us to look at slightly complicated problems. You won't see anything like this on an exam. I think there was a homework problem like this, but I think I might have even taken it out. So here it starts with the definition. The definition says two curves are said to be orthogonal if their tangent lines are perpendicular. So let me draw a picture just to give you an idea of what exactly we mean. So suppose I have, here's one curve like this. And suppose I have another curve, I'm gonna draw it like this. Now, let's compare their tangent lines. So I'm gonna look at the tangent line of this red curve, maybe looks something like that. And the tangent line of the blue curve maybe looks something like this. Now, if the tangent lines are perpendicular, so if the angle between these two tangent lines is a 90-degree angle, then these two curves, that red curve here and this light blue curve, are said to be orthogonal. Okay, so that's the definition. And so it seems random now, but this does have an application, I promise you, and I'll show it to you in 1 second. So let's solve this example. So the example wants us to specifically show that the family of circles centered at the origin are orthogonal to the family of lines that go through the origin. So what does that mean? I drew a picture here, or actually maybe I'll do a picture from scratch. So starting out with a circle centered at the origins. Okay, so imagine this circle is centered at the origin. I won't put the origin in. What we want to show is if you pick any point, so for example, I'm just going to randomly pick a point right here on the boundary. Just randomly pick a point. That's way too big. Pick a point, a small point. Now, if I find this, I want to show that the slope of the tangent line, so the slope of the tangent line would look like this. I want to show that this tangent line is perpendicular to any line that goes through the origin. So there, I've drawn a line going through the origin. I want to show this tangent line of the circle is perpendicular to the tangent line here of this line going through the origin. Obviously, the tangent line of a straight line is just itself, right? Because the slope is constant. So like for this line through the origin, it is its own tangent line. This line right here, that's the tangent line to the circle at that point, x naught, y naught. Okay, so I now want to just find the derivatives. So, slopes of the tangent line is just code for find the derivative. So I want to find the derivative of the circle. And so I don't know if you remember from geometry, but the equation of a circle is given as x squared plus y squared equal to r squared, where r is a non-zero constant, a fixed real number. So here I want to find the slope dy dx. And so I'm just going to take the derivative of both sides with respect to x. The derivative of x squared is just 2x derivative of x squared with respect to x. Derivative of y squared with respect to x is 2y, that's the derivative of the outside, times the derivative of the inside is dy dx. The derivative of r squared, since r is a constant, is 0. So after taking the derivative, I get 2x plus 2y times y prime, or dy dx equals 0. And then I solve for dy dx. When I move the 2x over, it becomes negative. When I divide by 2y, the 2's cancel. This is the generic formula for the derivative. I now pick a specific point. I now pick the point x naught, y naught on the circle. So I'm going to now evaluate the slope of the circle at the point x naught, y naught. According to this formula, the slope is negative x sub 0 over y sub 0. I'm just plugging in for x and y. So now I want to compare this slope with the slope of the line that's going through the origin. So we have this line here going through the origin, and it goes through the point x naught, y naught. I want to show the slope of that line is perpendicular. So the slope of the line that goes through the origin and the point x naught, y naught, as you know, you do delta y, rise over run, change in y over change in x. So you have y sub 0 over x sub 0. We see the slope of the tangent line of the line going to the origin is y sub 0 over x sub 0. And so, yeah, these two lines are perpendicular because this slope is the negative reciprocal of this slope. And so circles and lines form what we call an orthogonal family of curves, okay? And so the next question is, who cares? So what? So the thing about orthogonal families of curves that's really nice is that we can use it to define a new coordinate system. So let me just blank this out so I have some place to work. So here, if you look at the two-dimensional plane now, okay, so let me draw an axis here. We're looking at the two-dimensional plane. Any point in the two-dimensional plane, so now I'm going to randomly pick a point. So any point in the two-dimensional plane, so here's a point, can be identified as the intersection. So we can find a circle centered at the origin such that, okay, I know this doesn't look like a great circle. Okay, let me try again. This is the hard part, getting it to draw. I can find a circle centered at the origin. I should have drawn the circle first, right? Oh yeah, that's what I'll do. Let me draw the circle first. So for any point in the plane, what we can do is we can find a circle centered at the origin. Where's my circle? There we go. Here's my circle centered at the origin, and here's the point, okay? Imagine I drew this the other way. I drew the point first and then found the circle, but my drawing skills are terrible. So we can find a circle centered at the origin where that point is on the edge of the circle, and we can find a line through the origin that, again, my drawing is terrible, a line through the origin that goes through the point. And so now we can specify the location of the point by specifying the radius of the circle r and the angle of the line theta. And this point, we can identify it as the coordinate r comma theta, where r is the radius of the circle that it lives on, and theta is the angle that the line, through the origin makes with the positive x-axis and that point. Okay, so this will be called polar coordinates, and this will be a big part of Calc 2 and Calc 3, and it'll come up later and has to do with orthogonality. So that ends our discussion on implicit differentiation. So I now want to move to the discussion of related rates. So related rates is, again, implicit differentiation. So if you're keeping track, we did chain rule, we did implicit differentiation, which is really chain rule, and now we're doing related rates, which is implicit differentiation, which is actually chain rule, okay? So related rates marks the beginning of applications of the derivative. So one very important comment I need to make about calculus and derivatives, and the reason we're studying calculus at all, is that think about an equation from a pre-calculus class or an algebra class. For example, suppose I had the equation x squared minus 4 equals 0. In this situation, we know the solution is the square root of 4. So x equals plus minus 2. The solution here is a constant. So the solution of this algebraic equation is a constant. The reason we like calculus is if we look at, so in calculus, we look at equations involving derivatives. They're called differential equations. So differential like differentiable. So an equation involving derivatives is just called a differential equation, okay? So for example, here I'm just making up a differential equation, y double prime minus 4 equal to 0. Okay, so here I'm assuming y is a function of x. In this case, we will see, so you'll solve this problem when you take differential equations in a couple of semesters. We will see the solution of this differential equation is not a constant, but it's a function. And so this is really important because, you know, when I say the word constant, that's something that doesn't change. A constant is the same all the time. It's unchanging. However, derivatives are changing. And so we can use derivatives and differential equations to model things that move or change. So now, can you think of anything in the universe that changes or moves? You know, the fact is, everything in the universe changes, right? The only thing that doesn't change is the fact that everything changes. So this is why derivatives, calculus, differential equations are so important. Because with the introduction and invention of derivatives, we can write down equations where the solutions are functions that change, that aren't fixed. They can change in time or they can change in whatever your independent variable is. And so now we're able to actually simulate or model the real world with math that moves and changes, not with algebra, which is static and unchanging and, you know, not very useful in a world that's not static, that's constantly moving and changing. So related rates are applications of implicit differentiation. In related rates problems, the independent variable is time, and all the other variables are functions of time. And typically, we're trying to find, you know, the rate of one of the variables, i.e. the time derivative of one of the variables. So it's typically we use implicit differentiation and the chain rule to find derivatives of the form d dt, that is with respect to time. So the general, you know, guidelines for solving a related rates problem. Number one, these are word problems. So here we have to read the question very, very carefully. I would read the question 2 or 3 times and then try and make a sketch. Remember that the related rates problems are quite artificial and are usually based on some standard geometric shapes, triangles, spheres, you know, what have you. Now, reading the question is really important because all the information you're going to get is from the question. Actually, you know, for practice, I've read every question in the related rates section. I haven't solved every problem, but I've read every question just to practice the wording, just to get used to the language. In fact, I've read every question in every section because there's a lot of information in the problems. I haven't necessarily solved all the problems, but I've read the problems just to get that information, just to get my money's worth from my book. So list all the given information. So I also think of this as, you know, we need to know where we're coming from. Where we're coming from is what information we're given. Then identify what information we're trying to find. So I think of this as where we're trying to get to. So I need to know where I'm coming from and where I'm trying to get to. I need to know what information I know and is given, and I need to know what information I'm trying to find. Then find an equation relating the given information and the information we're trying to find. Then typically we will take a derivative using implicit differentiation, and then we'd substitute any given values and solve for the rate of change that we're looking for. So now I'm just going to do a bunch of examples because this is really the only way to kind of show you how this goes once I've shown you these basic guidelines. So for the first example here, you know, the reading is very, very important. That's why I would recommend you read it a couple of times. So here it says, the radius of a circular metal plate increases at a rate of 0.01 centimeters per minute when heated in an oven. At what rate is the plate's area changing when the radius is 50 centimeters? So it's perfectly normal for the brain to just kind of glaze over when it sees all these words flying at our head, okay? It's perfectly normal. Got to slow down and read the question a couple of times. Okay, So here now, when I go back and look and see, it says the radius of a circular metal plate increases at a rate of 0.01 centimeters per minute. Units are very important. These units tell me that they're giving us information about a derivative, specifically the derivative of the radius. So if I'm going to call the radius r, then what they're telling me is that dr dt equals 0.01. You know, the trick with the related rates is converting the English sentence into a mathematical sentence. These two are identical. These are saying the same thing. One is a statement in English, one is a statement in math. I would read them both the same way. The rate of change of the radius is increasing at a rate of 0.01 centimeters per minute. That's how I would read that equation. dr dt equals plus 0.01 centimeters per minute. So the idea of converting the English sentence into a mathematical sentence is really the trick here. So here, it says here, at what rate is the plate's area changing? So they're asking for a derivative. They want to know the rate of change of the area. So they're asking us to find dA dt. And then there's a second piece of information here. It says when the radius is 50 centimeters. So this sentence I can convert into math. So this sentence here, at what rate, we can convert that into math. It looks like this. Find dA dt, at what rate is the area changing with respect to time, when the radius is 50. These two statements are the same statement. One is an English sentence, one is a mathematical sentence. For us, we have to practice converting from the English sentence to a mathematical sentence. That's really the tricky part of related rates. Now all I need to do is find a formula that relates not dr dt and dA dt, but r and a. I want a formula that relates the area and the radius. To get to the derivatives, we take derivatives. Okay, so as you know, the formula for the area of a circle is a equals pi r squared. So here, that formula relates the variable a, the area, which remember is actually a function of time, and it relates the radius. Remember, the radius is a function of time. One thing you should really keep in mind is that the picture I'm showing you is false. The picture should really be where the circle is getting bigger and bigger as it gets heated. It should be a movie, the picture I'm showing you, because it's moving in time. What I'm showing you is one snapshot, in time. If you look at the movie, this is just one frame of the movie. Remember here, we're heating the metal plate and the circle is slowly getting larger and larger. That's what you should really be seeing in your mind, is an animated image. So now to me, this is the hard part. Figuring out what's given, figuring out what we're trying to find, and figuring out the equation. Now the rest of it is plug and chug. Starting from the equation that's relating, the variables of concern, I take the derivative with respect to t. The derivative of area with respect to t is just dA dt. The derivative of r squared, the derivative of the outside is going to be 2r times the derivative of the inside. The inside function is r. And we take the derivative of the inside function with respect to t. So the derivative of the inside function is dr dt. The derivative of r squared with respect to t is 2r dr dt. And now it's just algebra. Now what I need to do is not even algebra. I just plug in numbers right now. Now here I'm just going to plug in 50 for r and 0.01 for dr dt. So here, check out the notation. So here, in the function dA dt, I'm going to plug in 50 for r and 0.01 for dr dt. And so there's the function, and now I'm going to plug in all the numbers. And then I plugged in the 50 for the r and 0.01 for dr dt, and then I did the math. 50 times 2 is 100. 100 times 0.01 is just 1, and 1 times pi is pi. And so I get the rate of change is pi centimeters squared. The units here are important. I'm expecting to see the units of area, which here is centimeters squared, divided by the units of time, which here is minutes. And you can track the units. The units of the derivative, this 0.01, that's centimeters per minute. So here we're getting centimeters per minute, and the unit of the 50 is just 50 centimeters, right? So here, that's just 50 centimeters. Centimeters times centimeters per minute gives me centimeters squared per minute. And the way I would say the answer is I say the area is growing at a rate of pi centimeters squared. I want to keep in mind that the derivative is a vector. So here, if the answer I got was negative pi, I would say the area is decreasing at a rate of pi centimeters squared per minute. Here, we've verified mathematically that the area is indeed getting larger. So I say the area is growing at a rate of pi centimeters squared per minute. So that was an easy problem that I wanted to start out with to kind of show you the fundamentals. So now here's a slightly more complicated one. Again, we read and we read slowly and we read twice, So suppose the base of a 13-foot ladder that is leaning against a wall is sliding away from the wall at 5 feet per second. How fast is the top of the ladder sliding down the wall when the base is 12 feet away from the wall? Remember, if we don't know how to solve the problem right away when we read the question, that's okay. It's fine to not know. That's what we're going to figure out. So here, a lot of these related rates problems are based on simple geometric shapes. Here, the picture is going to look like a triangle. We've got the wall, we've got the ground, and this right here is the ladder. That's the ladder leaning against the wall. Yes, I'm writing ladder. Oh my God. And so now what's happening here, remember, this is moving in time. So what's happening here is the base of the ladder here is moving away from the wall. So this distance, if I call the distance between the wall and the base of the ladder, if I call this distance x, what's happening here is as the base of the ladder slides away, x is getting larger and larger. So this distance is increasing. So dx dt is a positive number. In fact, dx dt is 5 feet per second, because that's the speed at which the base of the ladder is moving away. And as the base of the ladder moves away, here, if I call this height from the top of the ladder to the ground, if I call this height y, as the ladder moves away, y decreases. Y gets shorter and shorter, because think about what's happening to the ladder here. It's moving, it's sliding away. That was terrible. It's sliding away here. And you can look at what's happening to x and y. Y is decreasing, x is increasing. In fact, this piece of information that the base of the ladder slides away from the wall at 5 feet per second, that's exactly the information about dx dt. So we know dx dt is 5 feet per second, because as the ladder moves away, that's increasing. So now here it says, how fast, so that's a derivative, is the top of the ladder sliding down the wall? So they want to know, how is y changing? They want us to find dy dt. And then it says, when the base is 12 foot away. So if you translate that into a mathematical sentence, it translates to find dy dt when x equals 12. This is exactly what this sentence here translates to, this whole thing. And that part's important. When we convert from the English sentence to the math, that's the tricky part. The rest of it, once you figure out what's given and what you're trying to find and get it into mathematical form, then it becomes much more of a standard problem. So now what I'm looking for is an equation to relate the x variable and the y variable, not dx dt and dyt, just x and y. Okay, if you look at the triangle, it's a right triangle. So one obvious equation to use is the Pythagorean Theorem. Here, clearly x squared plus y squared equals 13 squared. And now I can take a derivative with respect to t on both sides. So the derivative of x squared with respect to t is 2x dx dt. The derivative of y squared with respect to t is 2y dy dt. The derivative of 13 squared with respect to t obviously is 0. So here's what the derivative looks like. And now I'm trying to solve for dy dt because we're trying to find dy dt. So now it's algebra. I'm going to move the other term over to the other side. It becomes negative, and I divide both sides by 2y. The 2's cancel. And so here's my formula for the rate of change of y. It's basically the speed of the top of the ladder. And now I just have to plug in the given information. So let's check. Here, we're given dx dt is 5 feet per second. So that's no issue. We're told x is 12. So here I can plug in x equal to 12. What I don't know is I don't have y. So here, I might now have to do a little more math here to figure out, okay, but what's y though? This we're not given. But it's okay, you know, we can use this Pythagorean theorem. We can use x squared plus y squared equal to 13 squared to find y, because here we know x is 12. We're now going to assume x is 12, plug it in. And so if you plug in, you know, a common Pythagorean triple is 5, 12, 13. So here, or you can do the math. Here you can use the Pythagorean theorem to show that y squared equals 5 squared, and y is measuring a height, so it has to be positive. It has to be non-negative. So here, y equals 5. Mathematically, you know, if y squared equals 5 squared, y could be plus or minus 5. But here, practically, we can drop the negative root. So y has to be this non-negative number, 5. So yeah, now I can just plug in everything. So in my derivative, dy dt, I'm plugging 12 for x, 5 for dx dt, those were given, and 5 for y, that we figured out using the Pythagorean theorem. So there's my formula for dy dt. I plug in the numbers, some stuff cancels. I get the answer is negative 12 feet per second. So now here I want to be a little bit careful. I say thus the top of the ladder is moving down at a rate of 12 feet per second. I don't say the top of the ladder is moving down at a rate of negative 12 feet per second. That would be a double negative. You know, when I say down here, that's because there's a minus sign here. And I want you to think about the derivative is a vector. And so here, this minus 12 it's giving us direction as well as the rate at which the top of the ladder is moving down. So I could either say the top of the ladder is changing at a rate of negative 12 feet per second, or I could say the top of the ladder is moving down at a rate of 12 feet per second. I don't want to say the top of the ladder is moving down at negative 12 feet per second. That's kind of doubles up. So there's a second part to this question, and it asks, at what rate is the angle between the ladder and the ground changing when the base is 12 feet? So again here, if you look at the picture, it's referring to this angle here between the ground and the ladder. And as you can imagine, as the ladder is sliding down, that angle changes, right? That angle is going to get small. Eventually the angle should be 0, right? When the ladder completely falls down flat. So what they would like us to find now, you know, let's again practice converting the English sentence to a mathematical. At what rate, so they're looking for derivative, is the angle? So they want us to find d theta dt. At what rate is the angle between the ground and the ladder changing? So that's find d theta dt when the base is 12 feet from the wall, when x is equal to 12. And of course, don't forget, we still have this initial piece of information. So here, when they told us the base of the ladder that's leaning against the wall slides away from the wall at 5 feet per second, from our diagram as before, that's telling us dx dt equals 5 feet per second. So this is exactly that sentence translated. And when they say at what rate is the angle between the ladder and the ground changing when the base is 12 feet, that's exactly this find d theta dt when x equals 12, you know. And so now, all I need now is an equation that relates x and theta, not dx dt and d theta dt, just x and theta, and then I'll take derivatives. So here we're going to use some trigonometry. If you look at theta here, there's a couple of options. One option that I don't want to use, but I want to talk about is, certainly tangent of theta would be an option here. Tangent of theta is y over x. I'm looking for an equation that involves x and theta, and this certainly does. But I don't want to use tangent of theta equal to y over x because this is a little too complicated. Here, y is a function of t, x is a function of t. So when I take the derivative of both sides with respect to t, I'm going to need to do a quotient rule here. And then it gets messy. Then dy dt shows up, dx dt shows up. I'm going to have to use the answer from the previous part where we found dy dt. So tangent theta is a little too complicated. You could use it, but it's a little too complicated, so I'm not going to use tangent theta. I want to use something simpler. The simplest thing that I can see is if I do cosine of theta, then cosine of theta, if I'm not mistaken, is adjacent over hypotenuse. So this gives me x over 13. So this is an equation that has the x variable in it that I'm looking for, has the theta variable in it, and nothing else. Here, 13 is a constant. So when I do the derivative of x over 13, I don't need a quotient rule. So this is a simpler, certainly you could use secant also. With secant, you get the x in the denominator, which is kind of a little extra annoying. So here, cosine theta is the most straightforward function to use here. It's not the only one, but it's the most straightforward. So I'm using cosine theta equal to x over 13 as my function that relates the two variables theta and x. Now, take derivatives. Take t derivatives. So I take the derivative with respect to t. For cosine of theta, remember theta is a function of t. So here I have to do chain rule. The derivative of the outside is the derivative of cosine, which is this negative sine theta part. The derivative of the inside, the derivative of theta, is d theta dt. So that's where that whole expression on the left-hand side is coming from. On the right-hand side, the 1 over 13 I just copy down, it's the constant. The derivative of x here with respect to t is just dx dt. And so now, remember, I'm trying to isolate d theta dt, so I divide both sides by negative 13 sine theta. And now the last step is to plug in. I know dx dt is 5 feet per second, but I need to do a little work to figure out what sine theta is. Okay, but they've given us enough information. We know sine theta. So in general, the definition of sine here, so sine theta would be opposite over hypotenuse. So sine theta would be y over 13. And now, I don't know y, but I do know x. I know x is 12. And so using the Pythagorean theorem, I can solve for y. I know that when x is 12, y is 5. So now here I can plug in the 5 here, and I can find sine of theta. Sine of theta turns out to be 5 over 13 when x is 12 at this moment, at this instant. So now we've figured out everything. Now we can plug in all the parts. There's the derivative. Oh, I need a space right here, folks. I forgot. There needs to be a space right here. I'm sorry. This looks a little confusing. So this is an equation by itself. Sorry. That's one equation, and this is another. I need to stick a space in between these. So from the derivative here, I just replace the sine theta down here with 5 over 13. I replace the dx dt with 5. That's what was given in the problem up here. Dx dt is just 5. And then I do the math, and the answer I get here is that it's -1 radians per second. I was expecting a negative answer, right? That we're expecting that angle to decrease to 0. So here, we get a negative answer, and my answer in words is thus the angle between the ladder and the floor is decreasing at a rate of 1 radians per second. I don't say decreasing at a rate of -1 radians per second. I either want to say the angle is changing at a rate of -1 radians per second, or it's decreasing at a rate of 1 radians per second. So yeah, I got one last one here. So with this lecture, y'all, I did way more examples than I had time to cover. I just wanted you to have a bunch of examples that you could look at, okay? Because you can tell it takes a while to go through these. So I'm going to try and go through this one and the next one, but I may run out of time. So typically when I teach this class in person, I get through this example and the next one, but you know, depending on how time goes today, I may not get through the next one. Okay, so this one's a little more complicated. And here, this involves knowing the formula for the volume of a cone, which you're not responsible for. If you needed that on a test, I would give you, you're responsible for basic formulas. Area of a circle, circumference of a circle, you know, volume of a cube or rectangle, stuff like that, and we'll talk about it. So, okay, let's read. Sand falling from a conveyor belt at a rate of 10 meters cubed per minute forms a conical pile. So right off the bat, when I see 10 meters cubed per minute, I go, aha, it's a derivative because it's meters cubed per minute, and meters cubed are the units of volume. So what they've given us here is they've told us dV dt, if capital V is the volume, they've told us dV, d capital V dt, the rate of change of the volume with respect to time, is 10 meters cubed per minute. You know, I'm thinking about how do we convert all of this into English sentences. And then there's another very interesting statement here. They say the height of the pile is always, the height of the pile is always 3/8 the diameter of the base. Let me convert this into an English sentence. So if I'm going to refer to the height of the pile as h, the height of the pile, so I write down the letter h, is, that's an equal symbol. The height of the pile is 3/8 the diameter. So they've given us two pieces of information. One, that dV dt equals 10. And two, h equals 3/8 the diameter. And so I've written this down here in my given column. So there's my conical pile, by the way. So here, it's a cone, right? When we say conical pile, we're focusing here, it's a cone. And so I've got this cone, you can imagine sand being dumped from above on top, you know, so the sand comes down here. That's what sand looks like, red lines. And then you get this pile of sand that's building up. So here, the base of the radius is r, and the height of the pile is h, and we're given this formula, the volume of a cone. In the homework, these formulas are on the inside cover of your textbook. So now, as I said, we're given dV dt is 10 meters cubed per minute, and here's that sentence. The height of the pile is 3/8 the diameter. The diameter is 2 times the radius. So I cancel the 2 and the 8. I get here, we're given that dV dt equals 10, and the height is 3/4. Oops. Yeah, Angela, go ahead. Did you have a question? Angela, go ahead. Okay, so for the radius, you know, here, if you read the second part here, we're asked, yeah. Are you, I can't hear you. If you're talking, I can't hear you.
I seem to have a problem with my headphone, but yes. What did you ask me to do again? Because the thing keeps cutting out. I'm not on the Ethernet. The Wi-Fi seems to be cutting out.
I just was wondering if you had a question because your hand was raised.
Oh no, I just happened to press the wrong keys because
No worries.
I'm so sorry.
No problem at all. So if we read what we're asked to find right here. So here it says, how fast is the radius changing? Right there, you should see a derivative. They want us to find dr dt. How fast is the radius changing? Find dr dt when the pile is, you know, 4 feet high or whatever. That's exactly when h equals 4. Again, here we're practicing converting the English sentence to a mathematical sentence. To me, This is the hard part. The rest of it is plug and chug. So I'm pretty much running out of time here. Let me just go mention one thing here. So before we take the derivative, so now I'm gonna, basically now we want to take the derivative of both sides of this equation with respect to t. But be careful, there's two variables here, r and h. These are both functions of t. I would have to use a product rule if I tried to take the derivative of r squared times h with respect to t. But the information they gave us that the height is 3/8 the diameter, which turns, which is this equation, h equals 3/4 times the radius. We can use that to get rid of the h variable. So here I plug in this h, I replace with 3/4 r as given in the problem. And now my function, my volume function, is purely a function of only the variable r. And now we can take the derivative of both sides with respect to t. I'll let you look at that. And then I have to, in this case, solve for dr dt. So in this case, I'm trying to find dr dt. So I solve for dr dt. That's dr dt here, and then plug in all the information. The only other piece of extra work I have to do is they tell us to find dr dt when h is equal to 4. However, there's no h in my equation, but I can calculate when h is equal to 4, I can calculate that r is 16/3 using this formula here. So finally, now I can plug in for everything. I can plug in for r, I can plug in for dv dt. So I plug in 16/3 for r and then square it, a 10 for dv dt, and I did all the algebra and I got this answer here at the end. Okay, and so I conclude the base of the conical pile is increasing at a rate, the radius of the base is increasing at this rate. All right, folks, I'm gonna have you look at the other slides on your own.